All right, I'll go ahead and get us started here. Um, Welcome, everybody. My name is Suresh Srinivasan. I'm the coordinator for the Minnesota Astronomical Society's Beginner Special Interest Group, also known as the BSIG. This is our first of our winter presentations because it's too cold to go outside. Though this winter has been pretty good so far. We haven't had any below zero nights yet. Uh, I'm going to introduce Bob King, Astro Bob, for people that don't know. Bob runs a really neat blog online, Astro Bob. Bob, I know you're on Facebook as Astro Bob. Do you just have a regular website for that? It's just astrobob.com or something?
No, it grew out of working at the Duluth News Tribune, so the site for it is actually on the newspaper website. And
Okay.
I do additional pieces though that goes strictly onto Facebook, so they're
Yeah, I see
available to
those.
everyone, instead of having to hit a paywall.
So I will say that Bob is an excellent visual observer, perhaps one of the best ones I know. He also has a love for Northern Lights. A lot, probably it seems like half of his blog posts are about Northern Lights these days. He's also an assistant, or I should say, an associate editor, right, for Sky and Telescope magazine. So you can see sometimes his posts on the S&T website, or he has articles sometimes that are posted in the actual magazine. So that's pretty cool. And like I said, he's a fabulous amateur astronomer. I don't know, Bob, in terms of objects, what your favorite objects are, galaxies or planets, or
Wow, there's, quite a few of them, but my favorite category of objects I might share with you, Suresh. Those are comets.
yeah, I was wondering about comets.
Yeah.
Yeah, comets are cool. So, Bob, how long have you been an observer now? 30, 40 years, maybe more.
Just a few more than that. Yeah, I started when I was about 11 and I turned 70 this year. So I guess that would be 59 years.
59.
Yeah, gee, it's
Wow.
finally out there in the open now.
So a couple of quick points before we get started here. Please, everybody, make sure you're on mute on the call. I will actually be muting myself for most of it. Also, please turn off video. That'll help with the transmission. The other thing I will ask is that people, if they have a question, pull up the chat box, which is at the bottom of your screens, and just put a question into the chat. And then when Bob pauses, I will ask the question for you, just to keep Bob's presentation orderly and efficient. I don't want him to have to forget where he left off. So, does anybody have any questions before we get started? Real quick. I see we're up to 22 people right now on the call, so that's a good number. All right, Bob. With that, I'm going to hand it over to you.
All right. Well, great. Thank you, Suresh. I appreciate that. And it's great to be here, everybody. Good to see you all here as well. Hopefully, I'll make it a few illuminating minutes on a very cloudy Saturday afternoon. So we'll start up here right away with the presentation. And let me share my screen. And see if we can start at the beginning. Always a good place. Evenings at the Cosmic Smorgasbord. Of course, as amateur astronomers, we're constantly hungry, whether that's for deep sky objects or comets or planets, or after we've been out for a couple of hours, you just get hungry and you want a snack. You probably have heard, I want to start out with just some news. You undoubtedly have heard, and maybe some of you saw this online, the asteroid Leona, which is about 45 miles or so in diameter, irregularly shaped, it crossed or passed in front of the star Betelgeuse in Orion. So that occultation occurred on the evening of December 11th. We couldn't see it here in our region, and it was cloudy in Florida. The only people who saw it were out in Turkey and some observers in Italy and Spain. And they recorded the occultation. It was expected because the asteroid size, its apparent size, about matched the size of Betelgeuse. It was thought that it would block the star for like 4, 5, 6 seconds. But what happened was more like annual eclipse. The star did not disappear, it just faded. So here's an example from an observer in Italy. Here's Betelgeuse. You can see it. There's Orion's belt. But there's Betelgeuse before, and then here's the after. And you're like, oh, okay, I can see the difference. It dropped from about 0.5 magnitude to magnitude 2.5. So it was briefly fainter, but it never completely faded away. So the asteroid, for whatever reason, maybe because of the orientation of the body as it traveled in front of Betelgeuse, it was an annular eclipse. And observers described it as seeing the star dim for like 2 seconds visually. Of course, they recorded a more detail using cameras.
Hey,
Here's a,
Bob,
yeah, go
just
ahead.
real quick. Can you move your cursor real quick on screen? I think there's a little slight delay from where you're speaking to where we actually see your cursor moving. Just
Oh,
FYI.
okay. Okay, thanks for that. I know I have a
Yeah.
slow internet connection, so I'm not surprised. So I'll move it just in case folks don't know where Betelgeuse is. It's this star, the nice reddish orange supergiant, and here it is during the occultation. So you can see a difference, and if you paid attention, you would have noticed it. But some of that was buried in the twinkling of the star, too. This is a time exposure where you can see Betelgeuse here at the start, bright, 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 and then there's sort of a constriction, a little neck there as the star faded, and then it re-brightened after the asteroid passed. And then, well, my gosh, we've got to have a little video too, so you can see it fade, and then it comes right back. So they're analyzing all this data right now to determine, pardon me, specifically, like how large the asteroid is, to get a more precise size, and also exactly what happened was the orientation, the reason the star did not disappear, even for observers close to the center line of this occultation. And so we'll have more information on this in the coming weeks as that data is crunched. But it's interesting that they predicted it correctly. It went on schedule, but there was a surprise here. The star was never fully covered. Suresh, as Suresh mentioned, when we talked about what I like to observe, one of my favorite things are comets. And one of the absolutely coolest comets that's visible right now is Comet 12P, Pons Brooks. This was discovered back in the 19th century by two observers. This comet is a periodic one, so it returns once every 71 years. It was last came by in 1953, and hey, we're all here to enjoy it in the year 2022, 2023, and perhaps longer. One really interesting thing about Pons Brooks is even back in previous apparitions, it was known for having outbursts. It would, suddenly go from, let's say, magnitude 16 or very, very, very faint. It would just blast up in brightness like 4 or 5 magnitudes. And it's great that it's doing that this apparition as well in 2023 and into 2024. This is a picture taken just like a week or so ago when the comet passed by the brilliant star Vega in the constellation Lyra. What a beautiful pairing that is. And it was just after the outburst, so you see a little bright inner coma and then the larger, fainter outer coma. Gorgeous image. This comet has had like 6 outbursts since the beginning of the apparition, starting in July when it was about 16th or 15th magnitude. And overnight, it bolted up to magnitude 11. And you could see it like no problem, even in a 6-inch telescope. When the night before, you need like a 32-inch. Here's another outburst. This occurred on October the 5th. And during an outburst, and it's what happens during an outburst is that instead of you usually don't see anything, and then the outburst happens, and it appears like the comet is like a star with a tiny bit of bright haze around it. So an outburst, you just see the comet originally as a star, and then over time, as that gas and dust expands outward and the coma grows, the comet gets larger, it fades. So during an outburst, a comet is very tiny looking, but bright, so easy to see. And then during time, as you can see here a couple of days later, the comet gradually fades. Here's a close-up. Of course, this got to be called the Millennium Falcon Comet for obvious reasons. Some people now call it the Devil's Comet because it has 2 horns on it. To me, it looks like a horseshoe crab. So anything you like, you can picture it in Comet 12P. And the reason we think, this is a nice close-up, here's the nucleus here buried in that haze. You can't see the actual nucleus, which is estimated to be like, it's pretty big. It's like 15, 18 miles across. And the reason why you get these horns on the comet is because the outburst, which occurred on this side of the nucleus, the sunward bright side, as that material streams back behind the comet, behind the nucleus is large enough to actually block the flow of the material. So it creates sort of a shadow behind it. That shadow is not like a shadow that you would cast in sunlight, but it blocks the material from streaming back right behind the nucleus and creates kind of a vacuum there. And that gives it that cool Millennium Falcon look. I made a sketch during another outburst, and this is a more recent one. There's been another one since, actually, on December 14th is the most recent. This happened on November the 30th. And through my this was so cool because the night before, all I saw was just this big glow. This was the expanding coma from the previous outburst. On the 30th, buried inside there, suddenly the inner coma was like this bright little star, little tiny disk. So this comet is just unbelievably entertaining, if nothing else, and always something new when you're watching it. And then gradually that outburst expanded. All of this stuff is powered by what happens inside the comet as the sun shines on it and it heats up. Material inside beneath the crust vaporizes, and it's got to find a way out of this comet's nucleus. And so it does by finding a crack in the surface and exploding outward as a jet of material into space. And that jet is filled with fresh dust and gas from the comet, which lights up brilliantly in sunlight. And that's why during an outburst, a comet appears small and bright. There have been outbursts of other comets too. This is nothing unusual. Comets are doing this all the time, which makes them so much fun to watch. This is Comet 67P, back when the Rosetta spacecraft was in orbit around it. And here you see coming around as the nucleus rotates. Here it is. Look at that jet. Unbelievable. So we would see something like this at Pons Brooks if we could get up close like we did with Rosetta. I want to move on from the comet and from Betelgeuse, just to touch on the aurora and things aurora. This is a photograph of our planet from space in ultraviolet light. And here you can clearly see the two ovals of auroral light. These are boreal, the southern lights, are aurora austrinus, and then the aurora borealis right up here. This is where the aurora concentrates around the north geomagnetic pole in the polar regions of the planet, Antarctica, northern Canada, and so forth. So these are the two ovals. And we recently had an aurora on the night of December the 13th. This was the same night. And maybe you guys didn't see the aurora depending on where you live, but I bet you saw a bunch of Geminid meteors. So I was out taking pictures of the Geminids in the northern lights, and I happened to be facing in the same direction. And wow, there was the northern lights, and then right below it, there was this Geminid fireball that was, whoa, one of those ones where you just had to kind of shout out loud. So that was a wonderful thing. Now, the reason I bring up the aurora, also I should remind you that in the forecast for tonight from the Space Weather Prediction Center out of Boulder, Colorado, they're calling for a moderate to strong storm. So if we get really lucky and it clears up tonight, we'll have an opportunity perhaps to see the northern lights. It should be a really good show. I see the coronal mass ejection from the sun has already arrived. The numbers indicate that it's here, and it's kind of jazzing up the magnetosphere as we talk. So conditions look good. Of course, the aurora is not Earth is not the only place that has northern lights. I'm writing a book about the aurora right now, and as part of the research for that, I learned that every single planet in the solar system, except Mercury, just because it doesn't have an atmosphere, has northern lights. So, and I wanted to highlight one of those bodies, the planet Saturn. Here's a Hubble view of Saturn, and you can see, just like you saw with the Earth, the northern oval and the southern oval on the planet Saturn. Saturn's lights grow brightest in the ultraviolet range, which is the filter that Hubble used to take this picture, and a couple of other pictures I'm going to show you as well. Here's two other views where you can see the oval, just like the Earth. Here you've got material that arrives via an explosion on the sun. It could be a filament ejection or a CME from a flare, funneled down into the upper atmosphere by either planet's magnetic field, where it strikes the atoms, causes them to give off light and create the aurora. This is, even though it doesn't look like much, it's still one of my favorite little videos. This is visible aurora. So Saturn has ultraviolet auroras, but they are strong enough to produce some visible light. This was taken by Cassini, this little animated GIF from Cassini in 2017. And here you can see these are stars moving across the field of view. And there's the northern lights. Doesn't that even look familiar? If you've seen the aurora, you know it kind of comes like that in waves and in curtains. Scientists were able to determine using color filters what the colors of aurora are like at Saturn, and they are different from the colors on the Earth because the two primary elements or gases involved here are oxygen and nitrogen, and they glow. Oxygen's green and red, nitrogen is pink and purple and blue. On Saturn, hydrogen's the key atom because it's so rich in hydrogen. And those auroras were occurring at 870 miles altitude. And this is an image from Cassini, and we see red and then purple. Or I may have flipped this accidentally because I've got it purple on top. But just to give you an idea, if you could be on Saturn and you had a really great storm, you might see some colors caused by excited hydrogen atoms. I wanted to move on here now to Hubble's Variable Nebula. You might be familiar with this nebula. It's also called,
Hey, Bob, before
yes.
you move on, let me real quick. Does anybody have any questions about what Bob has discussed so far? I know Yara asked about what is an outburst, but I think Bob, you've covered that, I think.
An outburst, yeah, it's a term that comet users use a lot. It's a flare. An outburst is when there's a crack, or it's even can be a volcano-like feature on a comet surface, and the comet gets heated, and that vaporized ice from inside the middle of the comet has to find a way out. It shoots out that vent into space, and it carries with it lots of dust and gas. And that's what gets lit up. And that's suddenly the comet becomes so much brighter. And we call that an outburst. I hope that makes it
Very cool.
clearer.
Yeah, thank you. Does anybody
Mhm.
else have any questions for right now? Or all right, Bob, I'll send it
All
back
right,
to you.
great. Thanks, Suresh. Yeah, this is a familiar, I'm doing a lot. This is basically a potpourri today of some favorite things, some things that you can see right now, like the comet, for instance, and perhaps the northern lights. And this Hubble's Variable Nebula, which is shaped like a comet. Here we've got a beautiful reflection nebula. This is light, or I should say, this nebula is being illuminated by a star right here at the tip. This is actually a bipolar nebula. This is just one fan of the nebulosity. This one's pointed towards the Earth. It's being illuminated by a very young star there at the tip of the nebula. It has another end of it here going in this direction. It's not visible though because it points back into a dark nebula. So there's really two parts to this, but only one visible. And it looks remarkably like a tiny comet in your telescope. So I know a lot of you have probably already seen it. It's a bright object. If you haven't, please put it on your observing list this winter. It's just to the left of the constellation Orion, easy to find, and it looks just wonderful. This object's like 2,500 light years away. The star, which is called R Monoceros, I'm going to screw it up. R Monoceros, we're going to call it. It's in the constellation of the Unicorn, Monoceros, is in the process of formation. It has not yet entered what we call the main sequence, which is where the sun's been hanging out for the last 5 billion years. Nice, stable life, burning hydrogen in its core, fueling itself, illuminating the solar system. So we have a very young star in the process of formation that's forming from within this dust cloud. And the star is really invisible. It's hidden behind a ring. This looks star-like, but that you can't actually see the star. It's hidden behind a ring of dust, which prevents the light from shining right out into your eyes. And so the only way we can see the light from the star is from its poles, up to the upper right and to the lower left, the bipolar nebula. So the light is illuminating its birth cloud of gas and dust. I found this, I thought this was really cool. You can see here, the reason why they call it Hubble's variable nebula is because that ring of dust around our Monosaurotis, that ring of dust is moving, and as it moves, sometimes chunks of it block the light of the star, and the nebula becomes a little dimmer. Other times, there's clearer areas, more transparent areas, and then the nebula brightens up. So that's why it's called Hubble's variable nebula. The star itself is also variable, it gets brighter and dimmer. So this is a fascinating object to watch every single year, even every single month, and make sketches of where it's bright and where it's not. And you can make sketches and actually watch it change over time. Something that is not easy to see in a deep sky object because most things change on timescales that are just beyond human imagining. Here's another beautiful bipolar nebula. Again, two poles, top, bottom. And this was photographed by the Hubble Space Telescope. And in the core of it, there at that very narrow waist, is an entirely different star. This is not a newborn star. This is a red giant star. This is a star like the sun that will evolve into this enormous bloated red giant. And as it does, it gives off. It will just release and eject its outer atmosphere. And as it does, the white dwarf that will be exposed in the center of this, the former core of the star, will eventually illuminate the nebula to form what we call a planetary nebula. This one's in the constellation of Centaurus, so it's not visible from our region. And we have bipolar flows here. The gases shooting out from that star are moving at 100 miles per second. That nebula is expanding so rapidly that the temperature is plummeting in there. It's just like kind of how a refrigerator works with expansion and then you condense the gas again. When a gas expands, the temperature drops, but it's expanding so fast, the temperature has gotten so cold that this is actually the coldest place we know of right now in the universe. It's 1 degree Kelvin, which means it's 1 degree above absolute zero, the coldest temperature you can get. That makes it colder than the cosmic background radiation, which is a few degrees Kelvin. So sort of an amazing place, another bipolar nebula. Speaking of nebulas, we'll jump over into Orion now to look at a couple of things. There's one called NGC 1999. It is a reflection nebula. You have a young star here called V380 Orionis, and its light is illuminating all the gases around it. Again, this is birth material. This is what the star was created from. And now it's lighting up its environment for us all to see, but not this dark area. This dark area is situated so that the star's light does not illuminate it, but it is made out of dense gas and dust. It's called a Bach globule. And within that dense cloud of dust, that dark nebula, another name for those, within that dense cloud of dust, there are probably new stars forming the same way V380 formed. And when they finally are born, there's no doubt that that dark cloud will disappear because it will be illuminated by these newborns. So you can just see this through your telescope and bring that information with you and enjoy it that much more. Not far from NGC 1999, you've got the grandest of all nebulas in the sky for the Northern Hemisphere, I would say. It's the Orion Nebula, and it's 1,350 light years away. Right here, in the brightest part of the nebula, you can kind of see them in the photo. There are 4 stars there called the trapezium. These 4 stars, and in particular one of them, are responsible for illuminating this entire gas cloud. And they are brand new as far as stars go. 300,000 years old, give or take. And it's they're just amazing, and you can see them even in a pair of binoculars. They're scrunched together, but a telescope shows them very nicely. When you look at the nebula, we see it in the scope as a flat object. But picture, if you can, imagine the trapezium, these four stars, tucked down into the folds of the nebula, and they have blasted away the gas around them to create a cavern or a gap. Let me show you what it kind of looks like here. This is just an illustration, but down here is the trapezium. Here's the Orion Nebula all around it. So when you picture it, try to picture the trapezium as being in a nest, in a hollow of their own creation from within the core of the nebula. And they are the biggest and the brightest and some of the newest stars among the at least 1,000 new stars that the nebula is birthing right now. It took me a few nights, but I made a detailed sketch of what I saw through my telescope of the trapezium and the area around it. And I've added some little nicknames here. I have the pillow. There's my corner lot, but here's the four stars that you can see in any telescope. But use high power on this some night. Go out and crank it up to like 200x magnification. And if the night is steady, that the seeing is good, you will see buried within those little models tiny stars. And each one of those is another brand new star that was just recently born within this stellar nursery, this giant star-making factory. Included in the view here is this big dark gap. That's another dark nebula, like you saw with the Bok globule in NGC 1999. And that has a lovely name. It's called the fish's mouth, and it sort of sticks up into the bright core of the Orion Nebula, which is called the Huygens region. So you got the trapezium, the Huygens region, and the fish's mouth, and then those little babies in there that you can see just barely poking out into view on a nice night. Well, as promised in the description, I wanted to share where the closest black hole is. You all love talking about black holes, and this is so far as I could tell, this is the closest black hole that I was able to get a picture of. But the closest black holes we think, and we don't have actual like physical evidence of this yet, but theoretically, they are in the Hyades star cluster, which is the closest bright star cluster to the Earth. It's only like 151 light years away. And it's right up there. You can find it using the belt of Orion. Here you have a detailed picture, nice astrophoto on the right. A recent study, this just came out in the last few months, has shown that the Hyades should not look the way it looks or have the mass it has based on data from the Gaia satellite. They've done modeling and simulations, and the current Hyades, the V that we see, that shape and the stars around them fit better if we throw in 2 or 3 black holes. So within this cluster, no doubt, when it was born, there were some very massive stars that later, as they ran out of fuel, collapsed, became supernovae, and evolved into black holes. So if you add 2 or 3 black holes or a couple black holes nearby the cluster that may have been ejected over time, it much better fits the current mass and appearance of the Hyades. Again, no physical evidence, but theoretically, this is where you might find your closest black holes, just 151 light years away. So that brings up the question, can you see a black hole? And of course, you probably have seen pictures of the black hole in the Milky Way, the supermassive one, and also in M87, the galaxy in Virgo. But you can kind of see a black hole, or at least the effects of a black hole on its environment. Maybe some of you have gone out and observed what are called quasars. And these are they look just like faint stars in your telescope, but they're actually these brilliant sources of light inside of very distant galaxies. Here's one of the closer ones. It's 3C273 in Virgo, and this is what it looks like in Hubble. But if you use a blocking tool, as you can see on the right side image, if you block out the brilliant light and take a very long time exposure, you'll see that the quasar is actually in the center of a galaxy. So what we're seeing there is actually a supermassive black hole. And around that black hole, there's a disk of material because it's always pulling in and sucking down anything that happens to get close. And as that material drops into the black hole, it heats up to like, I don't know, 1 trillion degrees. And it radiates tremendous amounts of light across the entire spectrum. So quasars, they could be incredibly different. And they're called quasars, by the way, because it means quasi-stellar source. It looks like a star. They can be incredibly brilliant across many, many light years just because we've got a giant black hole eating lunch, snacking regularly. Again, reminds me of amateur astronomers. And during their lunch, and as the material heats, they will eject radiation out the poles. And so if that black hole and its disk happens to be pointed in your direction, keep following me here, it's called a blazar. So it's the same thing. It's a black hole with a disk around it. It's sucking down stuff. But if that beacon of bright radiation happens to be pointed at you, we call it a blazar. And there are some blazars that are particularly bright that you can see in your telescope. The best one that I have ever seen is this wonderful name. We always see these names in astronomy, tough to remember them. B2-1308 plus 326. It's in the constellation of the hunting dogs, Canis Venatici. This thing is 10.5 billion light years away. I should not be able to see this object. It should be invisible. But it turns out to be that the black hole and its beam of radiation is pointed towards the Earth. And so when it gobbles up new material, that thing can flare and become as bright as magnitude 13, which puts it easily in the range of an 8-inch telescope. Back in 2022, I watched this thing go from a historic high of magnitude 13.1 in just a matter of nights, drop all the way down to 15th magnitude. And right now, it's back up to 14. And most of the time, it's down at magnitude 18. So this is a very rewarding object. Plus, if you're looking for a long distance record for your telescopic observing, B2-1308 326 is the way to go. If you want to take a picture of this down here, if you want to get a map, because you need a map to find a stellar object, right? This is not a diffuse, deep sky, sizable thing. Just there's where you go. More information and a map down there. This
Hey,
is some.
Bob,
Yeah, go ahead.
do we have any explanation for why it brightens and dims like that?
It depends upon what's going down the gullet. All right. So if something large happens to be passed by, it goes down into the black hole. That thing gets ripped apart as it's swirling down into that disk and heated. It really does. It gets frictionally heated. And that radiates tremendous amounts of energy. You're turning mass into energy right there inside this black hole. And so if not much is happening, there's very little material going in, this object might be down here at around 19th or 20th magnitude. Look at how faint it is. But if something falls into the hole, hey, bingo, then you've got a source of radiation and that beam brightens. And now you can see the blazar. Quasar, blazar, basically the same thing, just orientation of the beam. So this one shows. Does that answer your question, Suresh?
Yeah, perfectly. Thank you.
All right,
Does
thanks.
anybody else have any questions right now? Yara says, it seems like recently it had a lot getting into it.
Yeah, right. Well, sometimes it was probably Thanksgiving. You tend to overeat. So we have so I'm just kind of jumping around here. Now that we've talked a little bit about quasars and galaxies, we've got galaxy clusters. There are particularly a large number of galaxy clusters visible in the fall and spring. But there are galaxy clusters visible now as well. One of the more famous ones, I guess, is Able, I can't read it myself, 426, I think it is. It's in the constellation of Perseus. And in that cluster, not that you'll see all of these, but there's like over 1,000 galaxies. Galaxies love to form clusters, just like stars are born in clusters. Galaxies can be born that way or gravitate over time to form clusters. And this one, you could see in an 8-inch scope or larger, a number of different members that look like tiny little fuzzy spots all near one another in the sky in the same field of view. And one of the brightest members of the group, and maybe the most interesting, is NGC 1275. This has a supermassive black hole. Now, most black holes, the majority are like, they're formed, they're only a few miles across, right? They're just formed from the collapse of a single star. But sometimes black holes can gather together and form one supermassive one. Gravitationally, they can drift into the cores of galaxies, form an enormous supermassive one. This one has the mass of 800 million suns. It's right out there for you to view the next clear night. At least you'll see the galaxy. And then galaxy clusters, and I've never seen this. And I don't know if anybody has ever seen this visually through a telescope, but look at this galaxy cluster. It's called Able 370. This thing is 4 billion light years away. And you can see ordinary galaxies in the cluster. You're like, yeah, those look familiar. But then you've got these stretched out galaxies, all distorted, apparently centered on the cluster. And what we're seeing here is something called gravitational lensing, where I couldn't find my big lens, but I've got this really tiny one. Here's like a lens, okay? And if you take a lens, it will focus and distort the background. So the galaxy cluster has so much mass that it acts like the lens I just showed you, and it focuses the gravitational weight of all of this, focuses the light of distant background galaxies that we otherwise would not see because they were too faint. It focuses them and brings them around into the view so we can see them. But like this lens, it distorts them too. They call it the funhouse mirror effect. So gravity brings them into view, but it also stretches them into these weird shapes, and that's called gravitational lensing. Einstein was the first to predict that this would happen. And again, amazingly, it was discovered many years later that this was possible when we began to take some really deep photographs of these clusters. Again, I know I've never seen any lensing myself, but maybe it would be visually possible with the biggest possible amateur telescope. I wanted to touch a little bit on novas. We don't have any current bright novas. You're probably familiar with a nova, meaning new star. It's not really a new star. It's an eruption that occurs on a very old star. This was one of the brightest ones from back in 2013 in Delphinus. If you could zoom in up close to a nova, you would see that it's actually a binary, two stars. One, typically a red giant or maybe even a sun-like star, and then around it is a very tiny, very dense, very strong, strongly powerful with its gravity, white dwarf. And the white dwarf is orbiting so close to the red giant that it's siphoning off its gas. That's hydrogen helium gas. And that gas forms a disk, a whirlpool-like disk around the dwarf. Over time, some of this material can funnel down right to the surface of the white dwarf. And when enough material has accumulated on the surface from that red giant companion, it gets heated to such a high temperature. You got to get enough material to get the pressure going. That thing gets heated and a thermonuclear reaction occurs and the whole thing burns. It just burns off that material all at once like a flash. And that is what a nova is. When that material goes thermonuclear, it explodes. It does not destroy the white dwarf. The white dwarf lives on, continues to pull matter. Some white dwarfs have repeated outbursts, and those are called recurrent nova. So it gets rid of the current bunch of gas it's pulled off from its companion, and then it accumulates more that falls to the surface, burns again, another blast. Well, that that is all to tell you that next spring we expect a very famous recurrent nova called T Corona Borealis, in Corona Borealis, the crown, is shaped there like a little cup. Here's T right down here. It last erupted back in 1946, and it became the brightest star in Corona Borealis. It was like second magnitude. And it's expected, based on its behavior right now in the past couple of years, it's predicted to erupt again next spring, like maybe April, May, and it could reach magnitude 2 again. So this would be a very bright nova-like explosion. And anybody could be the first to see it. You might be out right now at 5 o'clock in the morning looking for meteors or aurora, and you see corona and you're like, hey, what is that? There's a new star there. That's what it's going to be like.
Hey, Bob,
Yeah,
just real quick, back on that previous slide. Um, when you look at, like, say, supernova, they kind of move along a predictable brightness curve. Do we know how
right.
long roughly this one will stay bright for a nova?
Oh, I,
Like it
I didn't
erupts
check
the
it.
second magnitude?
Yeah,
Like,
novas usually they have predictable curves as well, Suresh. I don't recall what T's was back in 1946 during that eruption, but they typically have a jump, and sometimes a little extra peak and then that gradual drop with fluctuations. But yeah, there are light curves for novae, just like there are for supernovae. That's a good question.
thank you.
Mhm. We know, or at least we feel pretty confident about this prediction, because in the 1940s, here you see 1940s on the bottom, here you see the magnitude. Before the eruption, it dipped. It dropped from its typically 10th magnitude. So you could see this thing in a 4.5-inch scope. Then it dipped and then shot. Boom, we had the nova explosion. Okay. Here's the current time. 2005, 10, 15, we got the dip. It's starting to dip. So the prediction is, at least the most recent one, this says 2025 up here, but the current prediction is spring of 2024, based on the same or very similar dip that happened back in 1945. So it's great. I mean, I hope it happens. I always look at the star just in case. Easy enough to find and fairly bright too. Getting closer to wrapping up here, I did want to talk about, as long as we mentioned novas, and Suresh, you'd asked about that, and talk about supernovas. I wanted to talk about supernovas for a moment. Here you have a little illustration showing you how everything starts in dust and gas, nature's favorite ingredients for creating the most beautiful objects in the universe, including us. In an average-sized star, like the sun, as it ages, it will start burning from hydrogen. It'll burn helium and expand, become a red giant, and then slough off that outer atmosphere. And then you have a remaining little white dwarf star, like you saw in the nova, with a glowing, beautiful planetary nebula around it. Now, if you're a massive star, as you age, you become even bigger than a red giant. You become a red supergiant. And you burn even more elements beyond helium. You go carbon and oxygen and neon and all these different things until you arrive at iron. And at iron, you can't really burn it into something else. And so the energy source that's been keeping gravity at bay all those millions of years is gone. And so the star collapses in on itself and rebounds after the collapse and just tears itself apart completely, becomes a supernova. Remaining after supernova sometimes are either a very tiny star the size of a small city called a neutron star, ultra dense, a teaspoon weighs like 1 billion tons, or you can go straight to black hole. So those are a couple of options if you're a supergiant. So when a star does explode that way, the explosion could be visible across millions of light years. So we had a lovely supernova, easily visible even in a 6-inch telescope this year. It was called Supernova 2023 IXF. It was in the Pinwheel Galaxy, M101. Type 2 just means it was a supergiant star exploding. There are other types of supernovas too, but we'll just stay with type 2 for now. But look at that, right there in the spiral arm, right next to some nebulosity. These are nebulas in that galaxy. So it's possible that it's related to those. Here's a supernova blast simulation. And here are the leftovers. Perhaps a neutron star in the center with an expanding remnant of material. It's called a supernova remnant. Here's a neutron star compared to a city. It's something you can get your arms around. It's a small but super dense object, the core of that supergiant. And just so that you know what something would weigh if you stood on the surface, a cheeseburger right here on the lower right would weigh over 453 million tons. So it'd be a great way to diet is to get on a neutron star because you could never pick up that juicy hamburger. One of the most famous supernova remnants is the Crab Nebula in Taurus. The supernova event itself, the explosion occurred back in 1054 AD. We have that on good record from Chinese astrologers at the time. Carefully insert this thing. It's a giant star that exploded, and it left a neutron star in the core and the remnant. I'm showing you this image because the nebula looks like it's pulsating. It's because it's taken over a couple of different years. So the gas cloud, the remainder of the star, continues to expand outwards. And you can see that expansion in these images taken, I can't remember the exact dates, maybe 20 years. Wait, there they are in the corner, sorry. 10 plus years apart. So this thing continues to expand. And now we're going to focus for just a minute right in there in the core. And in the core is that neutron star. And that thing is collapsed. It collapsed so rapidly and became so small that it spun up to an incredible rate. And now it's spinning and shooting beams of radiation into space. It's become like a cosmic lighthouse. Here's our lighthouse down here. The pulsar, which is basically a spinning neutron star with beams of radiation shooting out the poles. The pulsar in the crab is spinning around at 30 times a second. That's how fast that neutron star is going. And every time one of those little beams flashes by the Earth, we see the star brighten and then it fades. Here's the pulsar flickering. See if you can spot it. Right here. That's the crab pulsar, flickering back and forth as the beams alternately strike our eyes and then move away. Now, very recently, we've learned that heavy elements can be created when neutron stars, you can actually have systems where you can have two neutron stars orbiting one another. And as they orbit, they gradually lose energy, fall in towards each other, and merge to form a single larger neutron star. Or maybe they explode. But in the merger of the two stars, they explode, pardon me, I misspoke. In that tremendous explosion, many more complicated elements could be created beyond our current periodic table. And then those elements break apart and form some lighter elements, like lighter in the sense of gold and platinum. Here's a periodic table, and you've got platinum and gold and a lot of different elements that are heavier than gold. It's always been a problem in astronomy. How do we create these heavy elements? Supernova explosions can create maybe up to gold, but it just wasn't a satisfying explanation. What now looks like if you merge neutron stars and they explode, the energy creates very big elements that then decay through fission. They break apart to form elements that are gold and platinum and so on in the periodic table. And we all love the periodic table. It's so cool that I had to include this cartoon too. That must have been painful. A long day at the tattoo parlor. One final thing, we've kind of gone, from comets out there to nebulas, out to some very exotic things, but I'd like to wrap up with something simple and straightforward that you see every single night that you're out, twinkling. If you use the belt of Orion, you could point it to the star Sirius, which you know is the brightest star in the nighttime sky. And Sirius, especially when it's low in the sky, it is the best twinkling star of them all. And we know that white light is comprised of a rainbow of different colors. So as the light from Sirius strikes the atmosphere, all the different temperature air cells between you and the star in our atmosphere, they're slightly different temperature and density, and they refract or bend Sirius's light this way and that this way and that is what we see as twinkling. But since light's made of a rainbow of colors, each color gets refracted this way and that. So when you look at Sirius closely, you'll often see that it's twinkling in every color of the spectrum. So one night I went out and decided, let's get the camera out and see if we can capture as many colors as possible of Sirius. So I defocused and took a series of images where you can see just how colorful the star is as our atmosphere refracts each one of the colors of white light differently at different times. So sometimes it emphasizes the red, and you might see Sirius twinkle red with your eye. The next split second later, it turns blue or pale green or yellow. Really, one night I just watched for like 20 minutes, all the different colors in Sirius. The conditions were just right. The seeing was bad, Sirius was low. So there's just a lot of things that are up there in the sky that are so beautiful to look at and worthwhile freezing a little bit if you need to enjoy them in the winter. For me, I've Suresh, that's the end of my presentation.
Okay. Yeah, I was wondering if something had happened.
No,
Um,
sorry. Yeah, I just came back to the normal screen here.
all right. Does anybody have any questions or comments for Bob? Anything want clarified or anything?
Thanks,
Bob,
Mark.
that was an excellent presentation, Bob.
Oh, well, thank you. I hope it wasn't too much, but I started looking into things and I thought, oh, that would be cool too. So